Alright, there's a couple of crucial aspects about using this sort of pseudo-graphical approach to finding shear moment diagrams. One, make sure that you understand that you're using the American Designer Sign Convention. That means that we are looking at smiley face of the beam deflection in terms of positive bending moment. It also means that we're drawing the moment diagram on the compression side of the member. Right? So that's a key thing, and along with that, of course, are positive, negative shears, all that kind of stuff. Right? Now, if you're really into a bunch of just procedures and the steps, then you've got this all laid out for you. Steps for drawing the shear moment diagrams. Got to find those reactions first, and then how to draw the shear diagram and all the critical things. So all those things, that flow chart is there for you. Take a look at that if those kinds of things matter to you. Right, or are useful to you. Now, the other crucial important part is that when we get done with either the shear or the moment diagram, when you draw straight lines, you cannot freehand sketch these. You must absolutely draw them with an actual straight edge. If you don't, you're going to get 0 credit from me. And you know I'm a tough person, and I'll feel bad about it, but it's still going to happen. Right? So draw a straight line with a straight line, and usually when you do that, you don't really need to do these other things that are shown here in these circles, but these curves you definitely need to. When I look at those curves, I have no idea what kind of function is that, and that's what these numbers are telling us. Okay, so this number that's here says that that's a function of x. This one says it's a function of x squared. This one says it's a function of x cubed. That little x to the power, well, you know that n equals the power of the polynomial. And you know that when we integrate x to the n, we get x to the n plus 1, of course divided by n plus 1 too. Right? So that's how you communicate what's going on here, because you're not going to plot these curves exactly perfectly to scale. If we wanted to do that, we'd go to the computer to do that. We don't need to. This is a quick graphical way to represent what's happening in the beam, and so we can quickly also identify where the maximums are located. Right? So one of the things that then you can do, there's kind of an interesting fun game to play here. We've got a cantilever beam, and we'll be given a shear diagram, and notice that we've got straight line segments here, here, and here, and we're given several values that are going on. Now, when you do this, I do not want you to just plot this to scale like this, because you're not going to do that generally. You're going to lay it out quickly by hand using straight edges, and what you do, if this is a 40-pound shear here, you write 40 and 40 on either side to indicate to me that even if you didn't draw it perfectly flat, you intend for that to be 0 slope right there. Same thing down here, that would be minus 20, that would be minus 20 at that end, and over here you'd end up with minus 50 and minus 50, closing off, of course, to zeros. Right? This is what you want to do. You don't have to lay out all this grid work and everything else. Right? It's unlikely that you're going to draw it perfectly to scale. Don't try. Just get it approximately to a good quality scale is sufficient. Right? Now, from the shear diagram, we can go look at the moment diagram, but we can also go back to the load that created this. And that's by remembering what all of this stuff was all about, that dV dx equaled W. Well, if that's the case, the slope of the shear diagram is 0, then we have 0 distributed load right here. Whereas we do have a slope on the shear diagram in this next segment, and that's going to be a minus 60 over 6 feet, so that means we had a downwards applied load that was constant through that whole segment. And check out the units. 40 plus the 20, alright, so negative 60 divided by 6 feet would be a minus 10 pounds per foot. Here we have 0 slope, so therefore no distributed load, and here 0 slope, no distributed load. But we do have these discontinuities, right? And we know a discontinuity positive or upward in the shear meant that we had a force of that magnitude and in that direction. So there's your 40 pounds. Over here, at this location, we had another one going from 20 to 50 going downwards, so that would have had to have been 30 pounds. And then finally we have a reaction that's equal to 50 pounds. See if that works out. 40 up minus 60 down would be a minus 20, and then 30 going down again, down to minus 50, 50 pounds taking us back up. Sounds like it works, right? Then we go to do the moment diagram, and it's the same kind of thing. dm dx equals v. So it looks like we're not told we have any applied couple out here, so we must be starting off at 0. We have a big change, positive change, 40 times 1 foot, 40 pounds that is, times 1 foot would be 40 pound-feet. So in that section, then we have a straight line, goes right up to 40. And then from there, notice we've got a straight line slope change on the moment diagram. That means we're going to have a parabola down here. Right? So that peak of that parabola is evidently right here where we have the 0 slope. How high does it go? Well, let's see. This is proportionality here. 40 to 20 is 2 to 1. Over 6 feet means that that was 4 feet, 2 feet. And so 40 times 4, 40 pounds times 4 feet would be 160 pound-feet, but it's a triangle, so divide by 2. So that's 80 pound-foot. So we end up with a net of 120 to get up to that parabola. Right? So we start off at 40 foot-pound per foot slope. Go back over here at the left side, and I just got to try to find a pretty good portion of the French curve that is tangent at the left and will get me to right about 0 slope where it's supposed to be. That's pretty decent right there. Right? And that's a second order curve in that section. Some people will put P for parabola. I like to put the numbers instead. Over here we'll have the same second order curve going downwards. And of course it's 2 times 20 divided by 2. So that would be, they'd go down by 20 pound-feet. And so that would be something like, I'd really like to be nice and tangent up at the top. Try to get this right. Well, you know something though? I need to be tangent here in this section too, right? It goes from 0 slope on the shear diagram, so constant shear means constant slope on the moment diagram. This area is minus 20 times 6, so that's a minus 120 pound-foot in that area. So that's going to go from 100 here to minus 120 all the way out there, and that's going to be a straight line segment. Notice how this is going to actually help me to find out or figure out how to draw this curve, because now I'm not only just matching 2 points, I'm actually matching slopes on both ends as best as I can so that I don't end up with a crown right there. That should be nice and smooth right at our max moment of 120. Okay, don't rely on the axis over here. Tell me exactly what it is. Right? And then out here at this end we have a sudden change in the shear, so a sudden change in the shape of the moment or slope of the moment diagram. The value, the change in moment equal to area under the shear diagram, 50 times 1, so that's another 50 down to 70, and so we end up with that minus 70. And note that our slopes, if we extended those tangents, represent the slopes, we get what I call the little bobtail or cattails that clearly indicate the break in the slope of that diagram, and evidently then we end up with a negative or a frowny face moment right here. And let's find out if that's really the reaction. We've got 40 times 1 plus, and that's times 14. It's 560 going this in a clockwise fashion. Minus, then I need to fix something here. It's already showing downward, so I don't need to put the minus sign. Opposite is, that would be going up if I had otherwise done that. So, all right, so 5, sorry. Let's do it this way. We got 30 times 1 plus 10 times 6 to get the load times this moment arm, which is 7 plus 3 times 10, would be 630. Remember, this was 560 going the other way. So bam, yeah, there's a net 70 from the loads trying to go that way, so that means the reaction has to be 70 opposing that. Okay, cool. Right? So that is a fairly complete, inadequate, and reasonable shear moment diagram.